So the idea is to presenting some procedure we have developed based on satellite images, remote sensing for, as you reported there, monitoring vegetation or providing, for instance, daily updated maps of the fire hazard or danger, because usually I was speaking about hazard, but they said that danger is more not hazard. Danger is more acceptable from people working in this field than danger. And also in the concern the distribution of fires in active fires. This is based on geostationary satellite. And other application that also the estimation of the burned area. These things, application concerns fire management. And the idea is also not just presenting the applications, but also the tools we are using to make this application operational. Because what I'm going to presenting is already operational. Good, bad, but it's operational, okay? As is reported there, we are using MATLAB, Python, gdal, this kind of softwares. And so I'm going also to show which the instruction that we are using to this. At the end, I'm just saying something about these services or products that we are providing, taking into account the possible improvement achievable by exploiting the next generation of Earth observation satellite imagery. Let us start from this daily fire hazard index or daily fire danger index. This index actually was in some way studied by the GRC in '98, starting from an index developed in the US from Burg and other scientists. The GRC is a European organization that is in charge of performing research for Europe. Okay? Then usually they got information from the European Commission on this request from them, they did the research. Then they decided to take this algorithm developed in the US and try to make something useful for Europe. Then they decided to choose this fire potential index that was developed in the United States. And the idea was to adapt this index for the Mediterranean forests. We started to work on this index on 2011. Tried to modify, the index was modified by us because we introduced it as the effect of the topography on the vegetation status, because of course we have to take into account as the sun is illuminating the vegetation, because this has an effect of the dryness on the dryness of the vegetation. Then some years later, we further improved this already modified index, introducing the live fuel moisture, because originally the index was only taking into account the so-called the equivalent moisture in the dead vegetation, not in the dead vegetation, in the dry vegetation, not in the green one. Then we introduced this index. In order to estimate this, the fuel moisture, we used this equivalent water thickness. That is an index that was developed, actually was developed from people working at GRC, was based on spot images, spot vegetation at the 1 kilometer spatial resolution. We applied this on MODIS images in order to improve the resolution to 250 meters. Then, you see the evolution. In 2019, we changed the name, because otherwise we cannot name modified. Then we changed the name in daily fire hazard index. in this one, we introduced the wind effect on the temperature of the vegetation. And finally, this year, we added some things to this index, introducing the life fuel moisture, but based on the European satellite Sentinel-3. That almost is something like MODIS. But you know, Europe is developing this satellite, then it's better if as Italians we are using, even because Italy is contributing to launch this, then it's better to use them. So this was just a short story of the index. The formula reported there is the one that we are using to extract this index. The first part is taking into account the part of the vegetation dried, and the other part is taking into account the state of the vegetation. Then in some way the humidity in the vegetation. The procedure. Let me. Since I'm going also to try to show the formula, I mean, not the formulas, the algorithms that we are using. First of all, the input data are this one. Then we are using MODIS. We are going to change MODIS with Sentinel-3, but I have to confess that for the moment it's easier to take MODIS images than Sentinel-3. But then we are using metadata provided to us from the Aeronautica Militare, because they are in charge of computing metadata for Italy. And from them, of course, we took the data that we needed, and temperature, humidity, wind speed, and so. This is given on daily frequency, of course, but the forecast data are for 3 days. Okay? Then the index is computed for 3 days, the present day, the day before, and the following day. And then other information needed are the historical NDVI value. We need 10 years of NDVI. Of course, the digital elevation model. And finally, also the fuel maps. Yeah, this is almost all. Then the NDVI, the data from satellite are used to estimate the NDVI, and also this GVMI, that is the one we are using to estimate the water thickness. Okay, then the water in the green vegetation. I think you have no problem about near or SWIR, what is meaning. Okay, no? It's clear for you that near is near infrared, the SWIR is shortwave infrared, and so on. Then this is this graph here is trying to show the process. Then from MODIS, you see in red, I put Sentinel-3, S3, so see that we are changing that. From that, we are computing this NDVI and GMVI. From that, we are computing this, they are used to estimate the green vegetation in the, and the water thickness in the green vegetation. From the point of view, from the metadata, you see, we are computing the evapotranspiration. The evapotranspiration was also introduced in this model in order to take into account the topography. Why? Because the formula used to estimate the water content in the dry vegetation was taking into account temperature and humidity that come from meteorological data. How we can introduce the topography? And the idea was to do this through the evapotranspiration, go through the FAO formula relating the evapotranspiration to the temperature, and then we do the inverse. So from the evapotranspiration, we try to compute an equivalent temperature that we can put in the formula for estimating the water thickness in the dry vegetation. I said this, I think it's quite complex, but it's done so you can think, oh, this very interesting thing, very complex. Okay, so we are also using, I said that we are taking a history of NDVI, fuel map, these things. The NDVI was used to estimate this relative greenness. Relative greenness is giving us an idea of how part of the vegetation is green, the part of vegetation that is dry, because it's considering the maximum value of NDVI in the last 10 years. Then, according using that formula, here actually is referring to 5 years, but initially we started from 10. Then the relative greenness is computed taking into account the actual value of the NDVI, computed every day using MODIS or Sentinel-3, and the minimum value in the 5 years, divided the difference between the maximum and the minimum in these 5 or 10 years, historical data. Then let me go on. Okay. Then the relative greenness is used to estimate the life vegetation. Then the part of the vegetation in the area of interest that is green. So let me proceed. Then we introduced another parameter to take into account the water present in the green vegetation, because in the original formula, the one developed in the US in '98, and then taken from the from the JRC, the European Center, they were just taking into account the dry vegetation. But of course, in the case of fires, also the green vegetation has an impact, in particular the humidity present in the green vegetation. Then in order to take this into account, we introduced this equivalent water thickness that is computed also this from the satellite images, according, as I said before, using this formula GM, the index GMVI. Actually, in case of Sentinel-3, now we are using a different approach, but the approach is based on the live fuel moisture content is computed starting from a simulation done with software like Prospect or Sile, I don't know if you know, because a software that allows to simulate the behavior of the vegetation according with the characteristic of the vegetation and the presence of chlorophyll, for instance, or the presence of water and so on. Then we are changing in some way the approach. Then we introduce this. This is just a comparison between, we introduced it, as I said before, in order to correctly estimate the effect of the topography. We introduced this, of course, the digital elevation model. The digital elevation model was used to estimate the evapotranspiration, because of course the evapotranspiration depends on the topography, because it depends on the time the sun is illuminating the particular area. And then this is just an example of the difference in the evapotranspiration between the case in which there was no topography included and the case in which the topography was considered. I think you notice Sardinia is one of the islands of Italy. Sorry. Okay, this then to estimate this equivalent temperature. And again, I said at a certain point now we, instead of using this equivalent water thickness, we introduce this live fuel moisture. let me, sorry, go very fast. One of the parameters for which we are using metadata is this one. Meteorological data are used to estimate the moisture in the small vegetation. No? I don't know how confident are you with the fuel maps, fuel models. Fuel models are models describing the behavior of the vegetation with respect to the fire. No? And the fuel, one characteristics of the fuel are the amount of vegetation at 10 hours, 100 hours, and so on. 10 hours means is referring to the size of the vegetation, means smaller is the size, faster will become dry. No? Then 10 hours means that in 10 hours it will lose much of the humidity. Now, this is an example of, then we are using Python now for taking automatically Sentinel-3 images. The images that we are using are already at level 2, then means that there is already a mask of the clouds are already masked, this kind of thing. In fact, you see the white area are area in which there are clouds. Of course, then we cannot use that information to develop our index. This is referring to, you know, now there are 2 Sentinel-3 as well. Also, we have also 2 Sentinel-2, 2 Sentinel-1. In fact, this is the Sentinel-3B, one of the 2. This image is referring to August 2022. The Python application is allowing us to download automatically the image. We have almost an image per day, like similar like Modis. Crop the image on the area of interest and then develop or produce what is requested to produce. This type of data are in this synergy is the name given to this kind of this level of images provided by Sentinel-3. In the synergy, because on the satellite on Sentinel-3 we have both optical but also still optical but thermal sensor also. Then in the synergy you can find both of them. Then you can easily combine them. We introduced another parameter that we introduced was also the wind, because we saw we were mostly working on Sardinia, because this part of the activity was done in the framework project funded by the Sardinia region. Then, of course, we take into account also what they know about what happened in Sardinia. We know then also the effect of the wind on fires. Then they know that for instance, when we have this Mistral, for instance, or Scirocco, there is more. The fire are more frequent. Then we introduced this sort of weight in order to take into account this different behavior of with respect to the wind of the phenomenon. This is an example. This is a map of this index, for instance, in May. Actually, in Italy, formally, the fire season starts in the middle of June. No? Then all the organization starts in the middle of June. Then from the middle of June to the middle of September. This is the period during which everything is organized in order to fight the fires. This is an image of May. Actually, as you see, in May there was no any hazard. The hazard, I mean, this is an index going, from 0 to 100. 100 means strong danger. Of course, 0 value, low value, less danger. You see, actually, in fact, in May there was no danger. In the other one is in 25 of June. Actually, you say 23, 24, 25. We're producing for the 3 following days. Of course, if we have meteo forecast for 7 days, we can also compute the same for 7 days instead of 3. Usually it is the forecasts are given for 3 days. You see, in this case, instead, we have some areas where the risk is, sorry, not the risk, the danger or hazard is quite important. Then it is just to say daily fire hazard reacts to raising of the temperature as we move from spring to summer. Our spring, I mean, our summer. Here, just I put as an example the C square IGI is the name of the project in which we were working. This was the simple few lines used to download automatically MODIS images. This is just using a VuGet instruction. Of course, it needs information concerning the, because you have to be registered, even to take Sentinel-3 or Sentinel-2 images, you don't pay nothing, contrary of this, the images of this morning. No, everything is free, but you have to at least register, okay? You can register as a student or a researcher, any kind of person can register, can take images for free. Then when you put the command VuGet, for instance, of course, you have to also provide the account and password of your account. And then you can put the time, the data you need, the area of interest, and from that you can download the almost automatically, because this program can run automatically every day, and then you can take the image of interest. Going back to this index, of course, we did a sort of a validation. First of all, on the side, on the left side, we see during the fire season 2021, last year, the distribution of the hazard, no? Because if you have all the island at high hazard, of course, it's not useful because it's the same like having nothing, no? The idea was when you have an information where the hazard is, who is managing this, we will send in advance someone to take care of the territory, you know, to monitor the area in order to be faster in supporting, in fighting the fire. Then you see in just the 5% of the region was considered at high risk, then small part of the country. If we are looking at the burned area, then the area where the fires occurred, you see, of course, the amount, the area, burned area that was assessed as at higher hazard is increasing. This means that the algorithm was, or the index was working quite well. Then the data produced, as I said before, are uploaded. Also, this is done almost automatically on a FTP site. You see, these are the different directory in which different products are, where who is providing the services, because of course, as a university, we cannot actually provide an efficient service. Why? Because, for instance, we have not power supply. Then if the electric power goes off, we cannot provide anything to anyone. At a certain point, we have no one in the laboratory. No? In the evening, people leave because according to the contract, is at 5 p.m. he should go out home. Then we are not ready for providing operational this in general. Then, of course, usually this is done in cooperation with some company because they are a little bit more flexible on these things. And then, for instance, in this case, we are providing this, let me call them products, so this information to the prime of this project that was a company using this FTP. Then from this, he was able to put the data in his own platform from where the user can take or can download or can look at. Here, for instance, we saw before how we can download MODIS images. Here is how we can download the Sentinel MODIS last time. Here, Sentinel imagery using this API, Sentinel SAT API. Then, of course, as I said before, first of all, you have to create an account on the Copernicus Open Access Hub. And then, using Python, you can, first of all, create a vector containing the starting time and then the time in which you are interested. Using the API, you can put your request to the Copernicus hub and then collecting the information requested. You can also specify the area of interest in order to reduce the size of the image that you are requested to download. Using this function in Python function, Claude said, named the place name to VKT. Then, using this Sentinel API API, okay, sorry, okay, sorry. You can ask, you can go on the web and collect the image in which you are interested. This is the same for, this is Sentinel SAT. Then this is useful for Sentinel-2 as well for Sentinel-3. Okay. And then this kind of function can work almost automatically. Then if you are you are requested to apply, to develop something that operates every day. Of course, you cannot do this by hand every day. Then you have to use something like this, something that can be made automatic. Okay, this is almost the same. Now you can also put the name of the products, where the product should be downloaded. At this point, you have your data downloaded, and then you can import, for instance, a GIS environment and proceed with the further processing. Another, I don't know if actually possibly this is not of interest in Argentina, I don't know, but another information of interest in Europe is the area where you can perform the so-called prescribed burning. Prescribed burning means burning vegetation in order to avoid strong fires, biggest fires. Actually, this consists in removing fuel, removing the vegetation. Removing can be done in different ways, cutting, thinning, removing, grazing, and so on. But in this specific case, we were thinking about prescribed burning, then this activity here. So burning the vegetation in order to preserve, for instance, nice forests or this kind of things. What is done for estimating this prescribed burning? The idea is to also, in this case, the area where the burning can be carried out in a safe way should be provided every day. Then also in this case, we have something that should run automatically. This was developed in the framework of this European project, PREFER. Then first of all, we have to identify where we have to apply this approach, this the removal of the fuel. Then we have to know, first of all, where the fires are occurring in the majority. Then in order to do this, we, first of all, we computed this HTTC, means homogeneous territorial classes. Then classes homogeneous in the area of interest. What we are using to estimate this, we are using, of course, the digital elevation model because they are impacting the fires amount and also the pericolo, the danger. Then the digital elevation model, slope aspect, the characteristics of the vegetation here given as fuel, and then also the climatic characteristic, the agroecological zones. The process is almost described here. First of all, using that information, we are trying to extract these homogeneous territorial classes, then introducing the history of the previous 8-10 fires, we can estimate which one of these classes are more the one in which the fire occur with higher frequency. Okay, this was done for the, of course, Sardinia region, but not because just because we were working in Sardinia. Sardinia is one of the Italian region more affected by fires because actually there are three: Sardinia, Sicily, and Calabria. These are the more affected by fires. In summer, also regions they have a lot of tourists. Then you know, we have to take care of the tourists, of course. Then the idea, using this, the digital elevation model, fuel, and so on, we were able to identify 1,440 homogeneous areas in general. Actually, in the region, there was a little bit less. But these are areas characterized by the same topography, I mean, the same height, the same slope, the same aspect, the same type of fuel, and the same agroecological zone. Then combining this map with the fires, the burned areas of the previous 8-10 years, we can estimate what is called the FPP, so fire propagation probability. Okay, so the classes of territory where fire occur more frequently. Here is reported the almost the different level of dangerousness. Very high, high, moderate, and low, and very low. This is giving us the, then this FPP is giving us the points where the area where the fires can occur more frequently, okay? But now we have to identify then possibly the area where we have to remove fuel. Okay. But of course, we cannot remove fuel on all the region. Yeah, it will cost a lot. And then the idea was to introduce some the areas more important, natural parks, urban areas, main roads, because at least in Italy, most of the fires are near roads because people that has put in fires, because 90% of the cases, the reason is human, in not just in Italy, Spain, Portugal, Greece. Also, yeah, I discovered this morning that also here, actually there is no reason, at least in Italy there is no reason, because there is a law of the 2000 was said that in the area burned for 15 years, nothing can be done. Then you cannot burn and then build your villa. your houses, because it's not possible. Then there is no reason for this. But still, the people have done. Then the idea is to identify the several relevant areas. Oh, sorry. Like roads, or then identify this buffer zone. 100 meters, we take some different buffer zones according to the area, and then in this way we identify where the removal of the fuel is needed. Then this is where the fuel is should be removed. This was the distribution of the hazard in this part of Sardinia that we were studying. That one was where, but when, because you cannot, the 15th of August in Italy, put the fire to remove the vegetation, because in that case, possibly you will burn all the island, because the temperature is very high, there is no humidity. Then this kind of practice is done usually in the winter time, from November to March. Italian, of course. Then there are some prescription. Prescription concerning the time, the temperature, the wind, humidity are reported here. There was a study done in Europe, funded by the European Commission, in which a group of scientists tried to define the requirements. So the prescription when you can apply this kind of approach. Then using meteorological data, we can identify when these conditions are satisfied, and then we can say for the next 3 days in this particular area, you can apply in a safe mode the prescribed burning. This was just an example of the information we are using, then the forecast of the for instance, humidity, relative humidity, temperature, wind speed, rainfall, and then based on that, we can estimate the area where that condition are satisfied, and then you can apply the prescribed burning. In this way, you can also discover, for instance, as in this case, that there are areas where you have these conditions. For instance, these are days in the winter, the days during the winter time in which you have the condition to apply the prescribed burning. You see there are areas like here, there, where you have just 1 day during all the winter time. Then of course, prescribed burning is not the right practice to apply in that area. Then you have to think to something else, removing mechanically or some other approach. This was also result coming from this process. Then what we are, apart the data, sorry, in this particular case, which is the data that are changing continuously, are the meteorological data, because the fuel map, I mean, the vegetation is that one, okay, can be dry or can be green, but it's from the point of view as fuel is always the same during the season. The topography also, we hope that nothing is happening changing the topography. Then the same for slope and so on. Then the only thing that is changing are the meteorological data, the only data that we are acquiring every day using for estimating our, producing this map. In this case, we are using, as I said, the Italian Air Force Meteorological Department data. You see, but they are at the resolution of 10 kilometers, because actually what they are providing is covering a quite large area, not just the Sardinia region, but also other areas. Sometimes 10 kilometers could be not good enough. Then we have also as I put as a backup, because sometimes the data are not coming for our problem, possibly because of internet problem or something like this. Then we are also using a model in-house. Then on one of our computer is running this weather research forecasting model. And then in this way, we can provide the same data models. We can produce meteorological data at 3 kilometers spatial resolution, because we are just working on the Sardinia region. And there you can see the difference in having 3 kilometers, 10 kilometers metadata or 3 kilometers metadata, of course. As the detail is quite better, of course, in the 3 kilometers case. Another, then let me change, this was before, then prevention. Then let us now say something about active fires monitoring, and then we will see the burned area estimated damage assessment. We are doing this geospot detection, of course, using geostationary satellite, waiting for constellation of satellite, low orbit satellite capable to provide an image every 30 minutes. So waiting for that, we are using geostationary satellite. We are receiving in the lab, in our lab, through this system called EUMETcast, that is provided by the EUMETSAT, that is a European organization that is managing meteorological satellite or geostationary satellite. Using this EUMETcast, we are receiving with an antenna of 2 meters this geostationary satellite from the European satellite, MSG, Meteosat second generation, and also we are also receiving the geostationary satellite of US, GOES-16 and GOES-17, and we are also received the Imawari, that is the Japanese geostationary satellite. Oh, we are using this, the so-called rapid scan sensor that is providing an image every 5 minutes. Then actually we have an image of Europe or Italy every 5 minutes, then almost we can theoretically cover continuously, no, the area of interest, because we have really an image of 5 minutes. Of course, where is the problem? Here you see this is MSG 10. This is the one moved on a little bit on the Indian Ocean. This is the one that we are using. In order to be faster, is just covering a part of the footprint. The problem, where is the problem here? The problem is in the resolution, because at our latitude, geostationary has a resolution of almost 16 square kilometers. Then means 4 kilometers by 4 kilometers, more or less. Then you can see the fire, but with this, the fire in this 16 kilometers can be everywhere. Then this is the one of the problem related to this system. But within the end of this year, hopefully, because it was expected to be launched in 2015, the Meteosat third generation is coming in, will be launched. And in this case, the resolution is of 1 kilometer. Then it's almost like MODIS, the thermal channel of MODIS. Then we can have a more accurate detection of the fire in terms of intensity of the fires, but in terms of geolocation of the fire, position of the fire. But we tried to solve this in a different way, using images provided by 2 satellites, then images acquired simultaneously from 2 of the geostationary satellites. Because which is the idea? The idea was in blue, for instance, you see in blue we have the grid corresponding to one of the satellites, and in green the one corresponding to the other satellite. If both satellites can observe, yeah, one is, I think, is open. Then if in this way we can, if the fire is detected in both Susanna. I continue. Okay, if the fire, for instance, is present in this blue, in the blue grid, according with its position in the green grid, this is we can see in which part of the pixel the fire is actually located. For instance, this is, in order to better understand, this is one pixel corresponding to one image. This is the other pixel corresponding to the other image. Assuming that the blue pixel is the one in which the fire is, okay? Of course, the information that the satellite gives is the coordinates of the center of the pixel, no? But if we know that the same fire is also observed by the other satellite, then it means the center is this one, okay? Then it means that the area should be this one. Then we can exclude this other area. So this is the idea. There is some example there showing us, in particular, you see in this case, before the correction given by the second satellite, the fire was actually identified here. With the correction, it was moved there. Okay, then you see, it seems that it's working because actually the burned area is almost where the red spot is, red point is. Also, we did also a comparison with MODIS. We see that putting the correction, the number of fires that have a correspondence with the MODIS fires is increasing. Then this was almost the idea. Procedure, how we are doing this. Then we are almost the software that we are using are reported there. We are using this MSG Data Manager, that is a software developed by a guy in the UK, Taylor is the name. It's a Windows program that allows to process this raw data coming from the satellite, then produce a full image in PGM format, and then that we can collect, we can convert in other format. This MSG Data Manager actually is a software that is commercial software, but the cost is around 100 euros, so very inexpensive. Then the other software we are using is so-called HSMSG. What is doing this software is cutting, because we are not interested in all the third of the world, the whole footprint of the geostationary satellite, but just on our small country or small island, Sardinia, okay? And then the thing that we are doing are cutting the image, converting in GeoTIFF, because we like GeoTIFF, not PGM, not NetCDF, not H5, HDF, GeoTIFF. Then we convert this in a GeoTIFF. From that, we extract the reflectances and also the brightness temperature. Then in MATLAB, but this, thanks to some of the people working with me, will be modified in Python, because I'm used to work, use MATLAB, but MATLAB is a commercial software. Then at the university, we are not paying for using MATLAB, but in general, you need to pay. Then using this MATLAB software, the system is processing this GeoTIFF several images and then detecting the anomalies. Finally, these anomalies are converted in shape files and then delivered to the platform where the data can be distributed to the users. What the information that the system is providing are given there. Then, of course, the coordinates of the point, the pixel identified as fire, containing a fire, the date, the time, the area of the burning area. This is based on all the approach of a certain dossier. Then it's based on using two channels to identify the estimating the area that is burning and also the temperature of the fire. For instance, in this case, 724. The temperature 304 is the temperature in the brightness temperature in the channel 4. Is also providing the FRP, the fire radiative power, that is an estimation of the intensity of the fire. Then this QC, that is a quality, an index of quality confidence index. 100 means that we are almost sure that what we have detected is a real fire, actual fire. And then this FRI, that is telling us how many times the same pixel was identified with a fire. Now, because since we have an image every 5 minutes, but the fire is lasting hours or days, possibly you will see the fire many times in that pixel. No, this was the... Okay, this was the process, but I think the most interesting is, again, this is just to show the advantage of a geostationary satellite, no? But you know this very well, so you can follow the events as it was something, as a sort of continuously. No? Then what we are using to do this, then there is this watchdog program that is waiting for the new image. When the image is arriving, is collecting the image and starts with the other processes. This one is the one that is clipping the image, is converting the image in GeoTIFF. Clipping then is cutting on the area of interest. Finally, this one, when all the images are in the right place, when I say all the images, I mean because we are referring, of course, to a multispectral image, then we need many channels. When all the channels are available, the system will start to process in order to extract the hotspot if there are hotspots. This is just to show in this, as reported in the operational service, which are the channels that we are using. So you see we are, the SFIDE is the name of the algorithm. Satellite fire detection. This is meaning of SFIDE. SFIDE, I don't know if is something that you are using. SFIDE means challenge in Italian. Then we are using from left to right, we are using the channel 1, that is at 0.63 microns, channel 2 at 0.81, channel 4, 3.9. And then we are also using channel 9 at 10 microns, channel 10, and channel 11. This is channels of the MSG satellite. This is a combination of these 3 channels, red, green, blue. Red, the channel 4, in green, channel 9, in blue, channel 10. Now, this is reported an interesting consideration can be extracted. Now, let us do this consideration. So you see that, for instance, in the north of Italy, no, on the Alps, we have almost, the area is almost red. Yeah, red means that the signal in the channel 4 is larger than in channel green and channel blue. Why? If we see in the visible, we see that actually they are very bright. Then possibly there are or snow or clouds. One of them. Then why the channel 4 in correspondence of bright areas as snow or clouds is giving a very high signal? Because the channel 4 around 3.9 micron is still affected by the solar radiance reflected by the surface, because still there is some contribution from the reflected. Then from the point of view of the sensor, the radiance reflected is still assumed as brightness temperature, as radiance emitted by the surface. Then as a consequence, channel 4 is providing a stronger signal. This is one of the problems that we have, because if we are not masking, for instance, a cloud, that cloud can cause a false alarm, no? As an increase in the temperature. what I omitted, because the idea was not talk about the algorithm. The algorithm is based on a sort of change detection. It's based on a comparison between the previous image, I mean, two images at 5 minutes, one from the other. If, of course, which phenomenon are faster? Fires and clouds, or the clouds could be there or could be not. No? Then one of the problems is removing correctly clouds. Yeah, this is. Of course, in order to reduce the false alarms that we have, we introduced some, apart the mask of Italy, in order to avoid the fires in the sea. That, you know, is easy to see that is wrong. We also introduced what we, you know, before we computed this FPP, fire probability maps. Then we can use that map in order to identify in the pixel or in the area, which areas, also in the pixel, which area is mostly potentially affected by a fire, in order also to try to improve the error in the geolocation of the fire within the pixel of 4 by 4 kilometers, apart the use of the two different satellites. This is some of the results, and we said before the information that we are providing are given there. There's a comparison between the fire brigades, Vigili del Fuoco, then the fire brigades data, the information coming from MODIS, available firm's website, the one provided by us, and also the one provided by EUMETSAT or EUMETSAT, because of course EUMETSAT has also developed its own algorithm for providing detecting fires. But as you see, in order to be very conservative, this algorithm is detecting very few fires. You know? These big points are representing the fires detected by this EUMETSAT algorithm. But you see, there are just two, but MODIS or our methods are detecting much more. No, the same. Oh, this is moving by. Yeah, okay, yeah. Sorry. Okay, but anyway, let me move. So as a suggestion, go on. This is an example of a comparison between MODIS and MSG, geostationary. This was a fire occurred in Italy in 2020. The fire actually lasts something like 2 weeks, very long. Also, just to show the difference between MODIS and the yellow square are representing the MSG pixels. So you see, very big. In the red circles, orange, are representing the hotspot detected by MODIS or VIRS, because you know now they are almost 4, no? MODIS, Terra Aqua, VIRS, NEPOIS, NOAA 220. I mean, they are 4. But if we look at this is the distribution of the FRP as function of the time. You see, in black, we have the FRP estimated from MODIS, VIRS, I mean, low orbit satellite. And the other symbol are representing the fire radiative power estimated from MSG. You see, in case of MSG, actually you can follow the phenomenon almost continuously. Instead of MODIS, the other, you have a series of information here, then a series of information some hours later. This is reported in a fraction of days, starting from the 3rd of July at midnight, and the same days later. Then the advantage of geostationary, of course, is the possibility to follow the event. Another interesting thing that you can do is you can estimate the burned biomass using, for instance, information taken from the FRP that can be converted in the FRE, the fire radiative energy. Then you can estimate the burned biomass, and you can also estimate the emission in the atmosphere, using some common coefficients, knowing the area that is burning, or then the type of area, forest in the area, sorry, the type of vegetation in the area. Instead, using, of course, the low orbit satellite, you can follow as the event is moving, because in case of MSG, you cannot see the fire moving, because actually the pixel is so big that the fire possibly can spend all the time in the same pixel, no? Even if it's moving in a direction or in the other direction. Instead, in case of MODIS, of course, you can, in this case, you see the color are representing different time. You see then, from this, you can say that the fires, for instance, was here initially, then from any reason moved on this other area. Ouch. But now it's going back. Sorry. Then is moving from that one to the other one. Then you can follow the also as the fire is moving in the area. Further, almost last, there is burned area monitoring. This was a project with funded by the Italian Forest Brigade. Actually, now they are part of the Carabineros, because they cross then they are called the Carabinieri Forestali. They are still devoted to take care of the environment, the forest in Italy, but mostly the idea is to, in order to have the law respected, then in order to take people that is doing, putting fire or this kind of, for pursuing the people. Then the idea was to make this estimation of the burned area using the Sentinel-2 imagery. Okay, the map there is representing the red square are representing the Sentinel-2 frames. Okay, then each one of that is one of the Sentinel-2 images. Then, as you see, they need almost 50 images to cover the whole Italy. In Argentina, I think there will be much more, of course. And then, of course, we have all these images every 5 days, no? Because the frequency of Sentinel-2, now that they are Sentinel-2A and B, is 5 days. This is the list of images needed. The color means that the same image is covering 2 different regions. These are all the Italian regions here. This code 32TMR is a code representative of the specific tile in the map. Then this is done, also this is done automatically. So the idea is not have anyone to check every day. Actually, this is not true because we have anyone, but still the idea is to have no one looking at what the system is doing. Then steps: downloading Sentinel-2 images, estimating. Of course, we are using the classical NBR index. No, we are estimating this. Of course, we try to mask clouds and remove shadows. Then we compare the NBR is compared with the one of previous day. Previous 5 days, then the previous image on the same area. Also, we are also registering if no data are available, because assuming you have the image 5 days ago. The image of today is cloud. Then you cannot estimate fires occurred from 5 days ago and today. Then you have to move to the next one. Then this should be, you have to take this in account in order to avoid to miss fires or burned areas. Then using the same index, we also assess the damage level, and then of course we produce polygon of this and then publish on our web GIS. Which software we are using? gdal, first of all, then with this function OGR to OGR that used for georeferencing, transforming, clipping, merging the images. We saw that the same region needs many, the same image needs many, region needs many images to be covered, no? Then you need to merge several images together, make a mosaic, and then estimate. Then OGR to OGR can be used for this. gdal warp can be used for reprojecting the image from OTM to, I don't know, VGS84, for instance. And gdal translate to also to compress the raster image. For instance, this is a problem in, just this is a curiosity, not, I said before, I'm using MATLAB because I love MATLAB. I mean, I'm confident with MATLAB. I think I'm able to do anything using MATLAB, okay? But MATLAB, when it's producing GeoTIFF, when you put GeoTIFF right, an image, even if the image original was, I don't know, 100 megabyte, can become 1 gigabyte. This is because it's double, is written in using 32-bit instead of 16. Or this, yeah. Then using gdal translate, you can recompress the image to at least 10 times. Then again, from 1 gigabyte to 100 megabyte. This is another way, because you can download Sentinel-2 using Python, as we said before, from the Copernicus hub. But there is a problem now that you cannot find in the Copernicus hub images, Sentinel-2 images older than 6 months. Okay? Yes? No, 6 months now. Then, but you can use this DIAS. You can use DIAS. DIAS as a system funded by the European Commission. Actually, there are 5. We are mostly using this on the DIAS because we are cooperating with the people that did this. On the DIAS, there is other on the DIAS, so there is also the other one is, how is called? Sorry, now I have something, I cannot record the other one. In the Onda DIAS, all the images are available, okay? All of them. Then you can also, in this case, you can download the images automatically. Of course, recall that in case of Sentinel-2, now we have Sentinel-1C, Sentinel-2A, then the level 2 is the one corrected, atmospherically corrected with other information. Since this was done from, for Europe from 2017, I don't know, for Argentina was 2018, no? Yeah. Then, of course, from 2018, you have both versions. Then the same done in Python on Sentinel Lab using Sentinel Sat API. Here can be done in a different way using the procedure reported here. Then through this Onda is almost the same. You have to register, you need an account. Also in this case, the registration is free, anyone can register. Then you can, using a sort of API also for this kind of system platform, you can ask and receive download the image in which you are interested. Then the processing is done in Python, because this was not done by me, otherwise it would be MATLAB. This was done from one of the people that is working with me. Then the Python is, what is important is given there, gdal, other OSs, other tools. The instruction needed to extract the Barnett area are almost there. When you have identified the Barnett area, you can estimate this delta, the delta NBR, then the NBR between the present image and the one previous 5 days before, or 10 days, depends on if no clouds are there. And you can estimate the damage using, this was an approach normally used, just estimating the value of this delta NBR. Actually, the level is are provided because you know, there was a long study done on this in US. Then almost the range used to the threshold used to provide the level of damage are almost done available on the literature, in papers. Then using this, according to the threshold given, you can estimate almost the level of the damage, the estimated level of damage. There was a problem, of course. The problem was that sometimes we were missing some Barnett areas because clouds before or clouds on the actual image or something else. Then the idea was to using hotspot provided from Pierce, Modis, and so on the one called the near real time, in which the data are available 3 hours at least, not more than 3 hours after the acquisition. Then what we are doing, we are receiving, we are collecting, also in this case automatically, these images. Not the hotspot detected by this low orbit satellite. We compare them with the Barnett area that we have detected in the same period, in 5 days. If there is any hotspot that is not accompanied by a Barnett area, we took or the previous image, previous of 5 days, 10 days, or the images after the actual one, in order to reanalyze the image. Also, this procedure, you see, I put MATLAB here because this was done by me. Then in this way, we were able to remove some of the, how we can call this, missed Barnett area. Okay, this is how the Python, the procedure in Python that is downloading the hotspot from films. Also, this is automatically done. The algorithm here is taking the hotspot, is grabbing on the area of interest, is converting, because the hotspots are given in text format, TXT, they are converting a shapefile using this procedure given here. And then, okay, just reported on in one case in one map of Italy. This is referring to the 18th of September of this year, last week. You see that this is just to show how the system is working. Then here is just, of course, also in this case, we did some validation, no? We compared our result with the one provided by the Carabinieri Forestali, one provided by other organization like this CIMA, and Kia Planet, because we are also requested by the Carabinieri Forestali to use Planet. I think you know about Planet constellation, no? I don't know who is connected, and I cannot say nothing about Planet. Then you see the comparison is very interesting. You see the yellow area is representing the burned area identified by the Carabinieri Forestali. Of course, the area could be not easily reachable, no? And then there could be a strong error in the estimation done by when you have to walk on the ground. We have several examples. The comparison is given in this table, but it's not the case. You see, we have in fact, in order to estimate why there was an approximation in the data provided by the Carabinieri Forestali, we also took into account the digital elevation model, no? Then, in particular, the slope, in order to see if it was due to the slope that was not making not easy to reach to cover the area. Okay, in many cases, other idea to remove the false alarms, because also the false alarms are also occurring in a part of the agricultural area, no? Because the area 5 days before could be green, then 5 days later there was harvested, then there is no vegetation, then of course. But we are lucky because forest brigade are interested in forest, then we can remove, using a land cover, we can remove the agricultural area, then at least this error is removed. Actually, they say, but sometimes the fire can come from agricultural, practice. I don't know if you have this practice. Yes, we have the same, no? In the after harvested, you put fire in order to clean. Sometimes the fires are starting from that. And then sometimes it's important to know from where the fire started, because, in order to ask people to pay the effect, the consequences. Then there are possibility to correct in some way in fact, in order to take into account as a consequence of the fact they asked us also to consider agricultural area, we did this probability. So moderata means bassa, low means possibly all the area burned was agricultural area. Then the fact that it was a wildfire is low. Moderate means that was both agricultural and forested area, and high when only forested area was interested by the fire.
Giovanni,
See,
I don't know how many more slides you have, but you have 10 more minutes in case
10
you
minutes.
want to leave space for questions.
Yeah, you are right. This then, when the things are produced, we are putting them on this web GIS from where the Carabinieri can take the results. It is done also almost automatically. Just very fast on this, because I said one of the topic was vegetation monitoring. Where is vegetation monitoring? So another activity also done in almost automatic way is this the early crop warning, but also vegetation early warning or crop early warning. Where is the difference in the resolution? This is done in medium resolution, means 300 meters. Of course, 300 meters, at least, this was mostly done for Africa. They have, in average, the size of the crop in the field is 2 hectares. Then, 300 meters are not good for 2 hectares. Then we did this using Sentinel-2. But still, we did also for at medium resolution in order to cover the whole countries, I mean, also the whole continent. How this is done? This is done introducing this VCI, Vegetation Condition Index, TAI, that is Temperature Anomaly Index, rain, also an index estimating the anomaly in the rain, in the precipitation. VCI is computed in this way, where maximum and minimum are the maximum and minimum of the NDVI, of the NDVI in the previous 6 years, if we are using Sentinel-2, because Sentinel-2 was launched in 2015, then almost 6 years. The other TAI, the precipitation, are computed using the last 5 or 10 years. Then based on this, we can estimate the anomaly in the temperature, the anomaly in the precipitation, the anomaly in the vegetation status. Then combining these things together, vegetation anomalies, rain anomalies, temperature anomalies, we developed this crop condition early warning index. This is also done almost automatically because the temperature is collected every day. The same almost for the NDVI when it was based on the MODIS. Now we have to wait 5 days if it's based on Sentinel-2. And this is just here the algorithm used. This is the so-called the pseudocode. But here, in particular, in one of these, the medium resolution is also based on the product provided by the Copernicus Global Service. I don't know if any one of you is looking at this. You see, in the vegetation, there is some of the products available in the vegetation are, for instance, the NDVI, but also the VCI, the Vegetation Condition Index. Actually, Vegetation Condition Index is not more provided by them, then we are obliged to do it by ourselves. Here there was a procedure to download also in this case automatically, what happened? Automatically, also in this case you have to register. And then you can download. These are just showing as the data are organized. Let me go faster. You can download using, for instance, instruction like this. This can be done also in MATLAB. Vuget is also working in MATLAB, but you know probably better than me. Then you can do also this in automatically. gdal to convert the data. We saw this already before. Then as the data are warped, or in this case using gdal, or merged if more images are needed to cover the area of interest, and also to resize the data. In this particular case, the data were uploaded on this platform that is, because this was part of this project that is an European project, then a European project called the Africultures, that is devoted to monitoring crop area in Africa. Okay, finished. This is the list of people in some way involved in this activity. Among them, you can see the well-known, your old master Pablo Marcialetti, that is still there with us. Okay, finished.